Stealth technology, also termed low technology, is a subdiscipline of military tactics and passive electronic countermeasures, which cover a range of techniques used with personnel, aircraft, ships, submarines, missiles, and satellites to make them more visible to radar, infrared, sonar, and other detection methods. It corresponds to military camouflage for these parts of the electromagnetic spectrum. Development of modern stealth technologies in the United States began in 1958, where earlier attempts in preventing radar tracking of its U-2 spy planes during the Cold War by the Soviet Union had been unsuccessful. Designers turned to develop a particular shape for planes that tended to reduce detection, by redirecting electromagnetic waves from radars. Radar-absorbent material was also tested and made to reduce or block radar signals that reflect off from the surface of planes. Such changes to shape and surface composition form stealth technology as currently used on the Northrop Grumman B-2 Spirit stealth bomber. The concept of stealth is to operate or hide without giving enemy forces any indications as to the presence of friendly forces. This concept was first explored through camouflage by blending into the background visual clutter. As the potency of detection and interception technologies have increased over time, so too has the extent to which the design and operation of military personnel and vehicles have been affected in response. Some military uniforms are treated with chemicals to reduce their infrared signature. A modern, stealth vehicle is designed from the outset to have a chosen spectral signature. The degree of stealth embodied in a particular design is chosen according to the predicted capabilities of projected threats. History. The concept of camouflage is known to predate warfare itself. Hunters have been using vegetation to conceal themselves perhaps as long as people have been hunting. In England, irregular units of gamekeepers in the 17th century were the first to adopt drab colours as a form of camouflage, following examples from the continent. During World War I, the Germans experimented with the use of selen, a transparent covering material, in an attempt to reduce the visibility of military aircraft. Single examples are the Fokker E-3 Eindecker fighter monoplane, the Albatros CI two-seat observation biplane, and the Linke Hoffmann RI prototype heavy bomber were covered with selen. In fact, sunlight glinting from the material made the aircraft even more visible. Selen was also found to be quickly degraded both by sunlight and in-flight temperature changes, so the attempt to make transparent aircraft was not proceeded with. In 1916, the British modified a small SS-class airship for the purpose of nighttime reconnaissance over German lines on the Western Front, fitted with a silenced engine and a black gas bag. The craft was both invisible and inaudible from the ground, but several nighttime flights over German-held territory produced little useful intelligence and the idea was dropped. Diffused lighting camouflage, a shipborne form of counter-illumination camouflage, was trialed by the Royal Canadian Navy from 1941 to 1943. The concept was followed up, but for aircraft, by the Americans and the British. In 1945, a Grumman Avenger with Yehudi lights reached 3,000 yards from a ship before being sighted. This ability was rendered obsolete by radar. The U-boat U-480 may have been the first stealth submarine. It featured an anti-joist-style rubber coating, one layer of which contained circular air pockets to defeat Aztec sonar. Radar-absorbing rubber, semiconductor composite paints and materials were used by the Kriegsmarine on submarines in World War II. Tests showed they were effective in reducing radar signatures at both short and long wavelengths. One of the earliest stealth aircraft was the Hortenho 229 Flying Wing. It included carbon powder in the glue to absorb radio waves. Some prototypes were built, but it was never used in action. In 1960, the first stealth technology development program was initiated by USAF by reducing the radar cross-section of Orion Q-2C Firebee drone. This was achieved through specially designed screens over the air intake. radar-absorbent material on the fuselage in a special radar-absorbing paint. In 1958, the U.S. Central Intelligence Agency requested funding for a reconnaissance aircraft to replace the existing U-2 spy planes, and Lockheed secured contractual rights to produce it. Kelly, Johnson and his team at Lockheed's Skunk Works were assigned to produce the A-12, the first of the previously top-secret Blackbird series, which operated at high altitude of 70,000 to 80,000 feet and speed of Mach 3.2 to avoid radar detection. Radar-absorbent material was used on U-2 spy planes, and various plane shapes designed to reduce radar detection were developed in earlier prototypes, named A-1 to A-11. In 1964, an optimal plane shape taking into account compactness was developed for another Blackbird, the Lockheed State Route 71. This aircraft surpassed prior models in both altitude and speed. The State Route 71 included a number of stealthy features, notably its canted vertical stabilizers, the use of composite materials in key locations, and the overall finish in radar-absorbing paint. During the 1970s, the U.S. Department of Defense launched Project Lockheed Have Blue, with the aim of developing a stealth fighter. There was fierce bidding between Lockheed and Northrop to secure the multi-billion-dollar contract. Lockheed incorporated into its bid a text written by the Soviet-Russian physicist Pyotr Yefimov from 1962, titled Method of Edge Waves in the Physical Theory of Diffraction, Soviet Radio, Moscow, 1962. In 1971, this book was translated into English with the same title by U.S. Air Force Foreign Technology Division. The theory played a critical role in the design of American stealth aircraft F-117 and B-2. Equations outlined in the paper quantified how a plane's shape would affect its detectability by radar, its radar cross-section. This was applied by Lockheed in computer simulation to design a novel shape they called the Hopeless Diamond, a wordplay on the Hope Diamond. Securing contractual rights to produce the F-117 Nighthawk starting in 1975. In 1977, Lockheed produced two 60% scale models under the Have Blue contract. The Have Blue program was a stealth technology demonstrator that lasted from 1976 to 1979. The success of Have Blue led the Air Force to create the Senior Trend program, which developed the F-117 principles. Stealth technology is not a single technology. It is a combination of technologies that attempt to greatly reduce the distances at which a person or vehicle can be detected, in particular radar, cross-section reductions, but also acoustic, thermal, and other aspects. Radar cross-section reductions. Almost since the invention of radar, various methods have been tried to minimize detection. Rapid development of radar during World War II led to equally rapid development of numerous counter-radar measures during the period. A notable example of this was the use of chaff. Modern methods include radar jamming and deception. The term stealth, in reference to reduced radar signature aircraft, became popular during the late 80s when the Lockheed Martin F-117 stealth fighter became widely known. The first large-scale use of the F-117 was during the Gulf War in 1991. However, F-117A stealth fighters were used for the first time in combat during Operation Just Cause, the United States invasion of Panama in 1989. Increased awareness of stealth vehicles and the technologies behind them is prompting the development of means to detect stealth vehicles, such as passive radar arrays and low-frequency radars. Many countries nevertheless continue to develop low RCS vehicles because they offer advantages in detection range reduction and amplify the effectiveness of onboard systems against active radar homing threats. Vehicle shape aircraft. The possibility of designing aircraft in such a manner as to reduce their radar cross-section was recognized in the late 1930s. when the first radar tracking systems were employed, and it has been known since at least the 1960s that aircraft shape makes a significant difference in detectability. The Avro Vulcan, a British bomber of the 1960s, had a remarkably small appearance on radar despite its large size, and occasionally disappeared from radar screens entirely. It is now known that it had a fortuitously stealthy shape apart from the vertical element of the tail. Despite being designed before a low radar cross-section and other stealth factors were ever a consideration, a Royal Aircraft Establishment technical note of 1957 stated that of all the aircraft so far studied, the Vulcan appeared by far the simplest radar echoing object, due to its shape, only one or two components contributing significantly to the echo at any aspect, compared with three or more on most other types. While writing about radar systems, authors Simon Kingsley and Sean Quegan singled out the Vulcan's shape as acting to reduce the RCS. In contrast, the Tupolev 95 Russian long-range bomber was conspicuous on radar. It is now known that propellers and jet turbine blades produce a bright radar image. The Bear has 4 pairs of large contra-rotating propellers. Another important factor is internal construction. Some stealth aircraft have skin that is radar transparent or absorbing, behind which are structures termed reentrant triangles. Radar waves penetrating the skin get trapped in these structures, reflecting off the internal faces and losing energy. This method was first used on the Blackbird series. The most efficient way to reflect radar waves back to the emitting radar is with orthogonal metal plates, forming a corner reflector consisting of either a dihedral or a trihedral. This configuration occurs in the tail of a conventional aircraft where the vertical and horizontal components of the tail are set at right angles. Stealth aircraft such as the F-117 use a different arrangement, tilting the tail surfaces to reduce corner reflections formed between them. A more radical method is to eliminate the tail completely, as in the B-2 Spirit. The B-2's clean, low-drag flying wing configuration not only gives it exceptional range but also reduces its radar profile. The flying wing design most closely resembles a so-called infinite flat plate, the perfect stealth shape, as it would have no angles to reflect back radar waves. In addition to altering the tail, stealth design must bury the engines within the wing or fuselage, or in some cases where stealth is applied to an extant aircraft, install baffles in the air intakes, so that the compressor blades are not visible to radar. A stealthy shape must be devoid of complex bumps or protrusions of any kind, meaning that weapons, fuel tanks, and other stores must not be carried externally. Any stealthy vehicle becomes unstealthy when a door or hatch opens. Parallel alignment of edges or even surfaces is also often used in stealth designs. The technique involves using a small number of edge orientations in the shape of the structure. For example, on the F-22A Raptor, the leading edges of the wing and the tail planes are set at the same angle. Other smaller structures, such as the air intake bypass doors and the air refueling aperture, also use the same angles. The effect of this is to return a narrow radar signal in a very specific direction away from the radar emitter rather than returning a diffuse signal, detectable at many angles. The effect is sometimes called glitter, after the very brief signal seen when the reflected beam passes across a detector. It can be difficult for the radar operator to distinguish between a glitter event and a digital glitch in the processing system. Stealth airframes sometimes display distinctive serrations on some exposed edges, such as the engine ports. The YF-23 has such serrations on the exhaust ports. This is another example in the parallel alignment of features, this time on the external airframe. Shaping requirements detract greatly from an aircraft's aerodynamic properties. The F-117 has poor aerodynamics, is inherently unstable, and cannot be flown without a fly-by-wire control system. Lockheed Martin F-22 Raptor and F-35 Lightning II are protected by stealth technology optimized for higher frequency targeting radars but not for lower frequency radars. Until now it was not a problem because low-frequency radars are unable to generate tracks for weapons. However, improved computing power are getting better and better at discerning targets more precise. So Lockheed Martin F-22 Raptor and F-35 Lightning II stealth technology could be inefficient during 2020 decade. That is why some aircraft manufacturer, like Dassault Aviation with Spectre on French Rafale, has chosen an active stealth technology. Similarly, coating the cockpit canopy with a thin film transparent conductor helps to reduce the aircraft's radar profile, because radar waves would normally enter the cockpit, reflect off objects, and possibly return to the radar. But the conductive coating creates a controlled shape that deflects the incoming radar waves away from the radar. The coating is thin enough that it has no adverse effect on pilot vision. Ships have also adopted similar methods. Though the earlier Arleigh Burke-class destroyer incorporated some signature reduction features. The Skjold-class corvette was the first coastal defense and the French Lafayette-class frigate the first ocean-going stealth ship to enter service. Other examples are the German Saxon-class frigates, the Swedish Visby-class corvette, the US San Antonio amphibious transport dock, and most modern warship designs. Materials: non-metallic airframe dielectric composites are more transparent to radar, whereas electrically conductive materials such as metals and carbon fibers reflect electromagnetic energy incident on the material's surface. Composites may also contain ferrites to optimize the dielectric and magnetic properties of a material for its application. Radar-absorbing material: radar-absorbent material, often as paints, are used especially on the edges of metal surfaces. While the material and thickness of RAM coatings can vary, the way they work is the same. Absorb radiated energy from a ground or air-based radar station into the coating and convert it to heat rather than reflect it back. Current technologies include dielectric composites and metal fibers containing ferrite isotopes. Paint comprises depositing pyramid-like colonies on the reflecting superficies with the gaps filled with ferrite-based RAM. The pyramidal structure deflects the incident radar energy in the maze of RAM. A commonly used material is known as iron ball paint. Iron ball paint contains microscopic iron spheres that resonate in tune with incoming radio waves and dissipate the majority of their energy as heat, leaving little to bounce back to detectors. FSS are planar periodic structures that behave like filters to electromagnetic energy. The considered frequency-selective surfaces are composed of conducting patch elements pasted on the ferrite layer. FSS are used for filtration and microwave absorption. Radar stealth countermeasures and limits low-frequency radar shaping offers far fewer stealth advantages against low-frequency radar. If the radar wavelength is roughly twice the size of the target, a half-wave resonance effect can still generate a significant return. However, low-frequency radar is limited by lack of available frequencies, by lack of accuracy of the diffraction-limited systems given their long wavelengths, and by the radar size, making it difficult to transport. A long-wave radar may detect a target and roughly locate it, but not provide enough information to identify it, target it with weapons, or even to guide a fighter to it. News poses another problem, but that can be efficiently addressed using modern computer technology. Chinese, Nansen, radar and many older Soviet-made long-range radars have been modified by supporting them with modern computers. Multiple emitters. Much of the stealth communications in directions different than a direct return. Thus, detection can be better achieved if emitters are separate from receivers. One emitter separate from one receiver is termed bistatic radar. One or more emitters separate from more than one receiver is termed multistatic radar. Proposals exist to use reflections from emitters such as civilian radio transmitters, including cellular telephone radio towers. Moore's law. By Moore's law, the processing power behind radar systems is rising over time. This will erode the ability of physical stealth to hide vehicles, ships, wakes, and spray. Synthetic aperture side-scan radars can be used to detect the location and heading of ships from their wake patterns. These may be detectable from orbit. When a ship moves through a seaway, it throws up a cloud of spray which can be detected by radar. Schlieren signature. Anything that disturbs the atmosphere may be detected because of the Schlieren effect caused by that atmospheric disturbance. This type of measurement and signature intelligence detection falls under the category of electro-optical MASINT. Quantum interference principles from quantum interference have been proposed for the detection of stealth aircraft. The overall approach relies upon devising a gravimetric radar system for detecting moving massive objects based on the time variation that these objects produce in the local gravitational field measured by several detectors. Acoustics. Acoustic stealth plays a primary role in submarine stealth as well as for ground vehicles. Submarines use extensive rubber mountings to isolate and avoid mechanical noises that could reveal locations to underwater passive sonar arrays. Early stealth observation aircraft used slow-turning propellers to avoid being heard by enemy troops below. Stealth aircraft that stay subsonic can avoid being tracked by sonic boom. The presence of supersonic and jet-powered stealth aircraft such as the State Route 71 Blackbird indicates that acoustic signature is not always a major driver in aircraft design. Although the Blackbird relied more on its extremely high speed and altitude. One possible technique for reducing helicopter rotor noise is modulated blade spacing. Standard rotor blades are evenly spaced, and produce greater noise at a particular frequency in its harmonics. Using varying degrees of spacing between the blades spreads the noise or acoustic signature of the rotor over a greater range of frequencies.